So today we are going to be talking about computer accuracy and how it pertains to linear algebra. So firstly, we need to start off with something called floating point. And that's how a computer interprets decimals. So let's talk about pi, 3.14. This part is always going to be represented by floating point. And this is because computers can represent whole numbers fairly well when they get really large, but once you get a lot of decimal places, like pi does, then it starts to have to cut some off. And where we start to see where it's going to cut off is about bit size. So, and we have two generally accepted that we're going to talk about today. It's called single precision, and double precision. Single precision has 32 bits, with 31 being determining the sign, so whether something's plus or positive or negative. 30 through 20 is going to determine the exponent, so basically how many decimal points there are, so like what's going over here. And then 19 through 0 are going to determine the actual numbers that are involved. And this one gives us about 7 digits past the exponent, past the decimal point. Double precision, which you could probably guess, is just double what single precision is. So 63 gives you the sign, 62 to 52 gives you the exponent, and then 51 to 0 gives you the number. And go figure, to give you about 15 digits. And this can also be 8 digits. And this could also be 16 digits. But this is the upper end. This is the upper end, and this is the lower end. So why is this important? Because this means that after this digit, we're going to be rounding, or we're going to be cutting it off. It also means that computers can't see anything in the 9th digit or 17th digits when it comes to these two things. So say we're doing a Gaussian elimination problem. And we have x minus 2y equals 3. And then we're going to say, just for the sake of this problem, that our computer can only read 3 significant digits. So 3 digits after the decimal point. That's all that the computer that we're working with has to offer. So 1.0004 minus 2y equals 3.0004. So to the naked eye, we can see x equals 1, y equals 1. But to a computer, this number doesn't exist and this number doesn't exist. So this is singular. And that means they're the same and completely wrong. This not equal, so it shows that there's a problem when they cannot read the discrepancy. Now you could always go to double precision, but that'll take longer. I mean, the answer to most of these problems are going to be get a better computer. The supercomputer that determined pi to a very large amount of digits about 7 years ago takes up an entire room. So get a better computer is going to be a very simple solution, but that's always going to take longer. So we're going to start to look at different ways that computers can truly make it better accurate for assumptions without getting a better computer. Now let's go into another example where a computer makes a mistake just due to how it represents notations. So y equals 1, x minus y equals 0. Now we're going to interpret this x equals y, so 0.001 x plus x equals 1, x equals a little bit over 1, because so x equals a little bit over 1, y would then equal, or a little less than 1, sorry, and y equals roughly 1 as well. Cool. However, our computer is going to read that because of how it has to, 1.0, because of how it has to write out things, plus x plus 1.0 times 10 to the negative 0, y equals 1. I think it actually does this to to 0. And then this will be 1.0 times 10 to the 0x plus 1.0 times 10 to the 0 y equals 0. Yes. Okay. Go. This is negative. So when it does its Gaussian elimination to get rid of this row, it's going to multiply. It's going to be negative 1,000 times P1 plus P2, which will give the second row equal to 1001 y equals negative 1,000. Well, I don't know why that's supposed to be y. Which gives us an answer that equals y equals, negative, this would be negative. Y equals roughly 1. However, in doing this means that the first equation equals 0. This then leads to the first equation equal x equals 0, which isn't right. Right, the x first equation equals 1. So what we do a thing called, excuse me, we do something called pivoting. So we're instead going to pick the number that is bigger to be on top, x minus y equals 0, and then instead of the smaller number equals 1. So that way you have a less margin of error when you're using this number. And then there's a system from MIT, system equation from MIT that really showcases this quite well. And we're just going to do a little bit of that. And so that way I can explain the entire process. 0, 1, 2, 1, 4, 0, 0, 100, 200, 800. Now, when you do partial pivoting, you're trying to look at this row. You're trying to look at the first row because we're trying to get all of this to equal 0. So we're looking at this first row, and we're looking at the absolute value of that row. Then we're going to put the largest number on top. So now we have 1, 2, 1, 0, 1, 0.02, 0.01, 0, 0. And then we have 0.02. And then we do Gaussian elimination like normal. I'm not going to go through that just on the sake of time, but you get an answer that equals 1, 0, oh, we should probably scroll down, 0, 0, 0, 2, negative 0.03, 1, 0, 2, 1, too many zeros here, that's what I thought. 0, 1, negative 0.02, 2, 100, and then 200, 1, 0, 0, 1, 0, 4, 800. And we're going to do the exact same thing again. We're going to look at this row. But we're going to exclude the top part because the top part's already done. Now we're looking at this column, this row, trying to get this to 0. So we're going to look at this column right here. We're going to see which one's tallest. Oh, it's 1. We're going to flip it. And this is, in all reality, this is just so you get numbers that are least likely to give you error because they're bigger. And so in doing that, you get 0, 1, 2, 1, 4, 0, negative 0.3, negative 0.02, 0, 0. Again, we're skipping the actual math part because in sake of time, like I said, and we get 1, 2, 1, 0, 1, zeros across the board here, 1, zeros across the board, 2, 0.04, 100, 1, 0.03, 200, oh, we should probably move this over a little bit, 1, for 0.12, 800. And now we have to do this one more time. 100 is obviously bigger than 0.04, so we're going to pivot again. Again, this just makes it so rounding errors are decreased from computers. This is the same process as a computer would be doing. It's just we're writing it out and we're going through the steps just so that you have a better understanding of this. 0, 0, 100, 200, 800, 0, 0, 0.04. I understand. I would probably manipulate this row, multiply it when I was actually doing my math. However, computers are always going to multiply this one. I couldn't tell you why. That's just more complex computer talk, in my opinion. So you get a final row that equals 1, 2, 1, 0, 1, 0, 1, 2, 1, 4, 0, 0, 100, 200, 800, because that row doesn't change really at all throughout this entire thing. And negative 0.2 line. And then we can solve, so this would be A, B, C, D. Cool. And then we can solve that D equals 4, and we can plug that in to solve the rest of the variables. So it just helps you reduce any rounding errors that you might do if you're working with very, very small numbers. And it really helps computers because, as we saw earlier, this answer is nowhere near the right one. Continuing on, computers also make mistakes when it comes to dot product. And the mistakes computers make with dot product, it ultimately revolves around rounding. When you do the dot product, which is x times y times cosine of theta, the cosine of the angle of the vector that x and y create, you're going to get a rounding vector. So we do the actual dot product as this, and then we represent the dot product made by computer as that. So these are not the same. Usually this one I think is less. So sorry, that one's greater. Scroll all the way down again. This one's greater. So how do you fix this? How do you fix this? What you usually do is you do this thing called blocking. You use the block method or the super block method. For block method. The super block method is just a more complex version of the block method that goes into a lot of computer science stuff that we don't need to know for this class. So the block method, what a block code does is it creates blocks, or a chain of blocks that are all self-referential. So this connects. And they have data, so say this was digits 0 through 7, this was digits 8 through 15, and this is digits 16 through 22. They have data, they have a unique fingerprint. I know that's really hard. And then they have the fingerprint of where they're referencing. Reference fingerprint. We'll put the fingerprint reference. So say this one, it has the 0 through 7 data. It has its fingerprint of 528. And it doesn't reference any fingerprint, so it has quadruple zeros. This one has its data of 8 through 15. It has the fingerprint of 627, and it references 528. This one has obviously 16 through 22 data. It has its fingerprint of 854, and it references 627. So that goes there, that goes there. And that way you can work around the capabilities of computers by having each one do a very simple sheet of code. So this is its own set of numbers. And then it can all be self-referential, so you eventually get a line that makes sense as an actual number. But why do we care? The greatest question in pretty much all of mathematics, in my opinion, because nothing really matters unless you can apply it. Do we care? Now, for Gaussian elimination, so how can these be applied? Through computers. We have pictures. More specifically, enhancement. And they use a process that is similar to what the dot product does, which is one of the reasons it's brought up earlier, so when you try to enhance a fingerprint, so you have a fingerprint, I'm not going to draw a fingerprint because I can't draw a fingerprint, and you want to enhance it so you're looking at this section right here. It's very taxing on computers to do all of this. So what it does is it breaks it down to little blocks, and then combines them all together to get an image using a software that not important for our purposes. And in doing so, it does the Gaussian elimination, I can't remember the name. It does partial pivoting. That's what it's called, It pivots. It pivots, and in all doing so, it creates a block of code that then this block of code refers to, and this one refers to, and this refers to, and that gives you a nice little image of a fingerprint and a close-up level that you want. Now the dot product in real life comes in one of my favorite things, video games. And one of the most simple ways I can explain this is, guard mechanics. Guards have a specific radius of, say it's 120 degrees. And you trying to be your sneaky self, and they have a vector going towards straight, and then they have you over here, a vector going towards you. And then they use the dot product, so x times y cosine of theta, and they solve for cosine here to get an angle for here. They solve for theta actually to get an angle here, and if that angle matches within the 120, which it would in this case, then you would be caught and seen by the guard. If not, then you obviously wouldn't, and it does the same sort of block coding aspect that we talked about earlier when doing these calculations. So that way you get very specific results, because what if I'm right here? If you're inaccurate and then it glitches and you don't actually see me, that obviously happens sometimes in video games. But the goal of the developer is to get it to be as accurate as possible, and in doing so, it's better to use block coding. I hope that helps people with your understanding of how computer accuracy is part of linear algebra. We use computers for a lot of what we do in class, especially do calculations, and it's nice to know that there are safeties involved for the inaccuracies that computers do.